We hane new updates on ThreeI Atlast. In the past 24 hours, the object has shown two significant anomalies that are now being reviewed by multiple space agencies. First, a photometric shift was detected, a measurable change in the object's brightness pattern, suggesting either surface variation or a change in how it reflects sunlight. Shortly after, NASA confirmed signs of non-gravitational acceleration, meaning ThreeI Atlast is moving in a way not fully explained by gravity alone. A trajectory update was released, and while the change is small, it is large enough to alter future projections. At this stage, the data doesn't point to a definite cause, but it doesn't match natural models either. Stay with me. We'll break down what changed, how it was detected, and what the revised trajectory actually means. They say space keeps its rhythm ellipses drawn by gravity, silence folded into prediction. But tonight, that rhythm falters. NASA's Jet Propulsion Laboratory has just confirmed it. The interstellar object known as ThreeI Atlast is no longer where it should be. Its path, once smooth, calculated, obedient to celestial law, has slipped. A deviation measured in fractions of a degree, but in cosmic terms that's a declaration of rebellion. You can imagine the screens inside JPL glowing faintly in the dark, thin lines of trajectory, bending like the curve of a pulse gone wrong. One new coordinate, one recalibration, and suddenly the solar system has a visitor that refuses to stay mapped. If you stood with us now in that control room humming under low fluorescent light, you would feel it, the quiet thrum beneath the data, the pulse of an anomaly. The numbers don't shout. They whisper a pattern, breaking a symmetry unmade. The update came during a government shutdown when most official channels were asleep. Yet David Farnocchia, one of NASA's orbital analysts, uploaded the corrected data anyway. Perhaps he knew silence in science can be louder than disclosure. The previous orbital charts showed a predictable curve inbound from interstellar space swing around the Sun exit toward the outer dark. But the new path, just a few arc-minutes adrift, suggests something else, a force not accounted for, a push beyond sunlight or dust. Imagine tracing it on a blackboard. The clean ellipse fractures, a single chalk line veers off, subtle yet defiant. That's all it takes for the known to tilt toward the unknown. From ground-based telescopes in Hawaii to the deep space monitors, orbiting Earth instruments blink in quiet disbelief. SOHO Stereo A and GOES 19 confirm the deviation. Even with error margins accounted for, the math holds. The object is accelerating where no propulsion should exist. You can think of it like a bullet gliding through molasses until suddenly it jerks forward, as if remembering an unfinished destination. A trajectory isn't supposed to have intent, yet ThreeI Atlast behaves as though it does. In orbital mechanics, such a shift would require a new vector of force outgas and collision magnetic drag, but none of these have been seen. Not yet. And so at this precise moment, the story of ThreeI Atlast ceases to be prediction and becomes presence. The question remains suspended between us and the stars. If gravity did not move it, what did? The Sun was supposed to end it. At 203 million kilometers, 1 1/3 times the Earth-Sun distance 3, Atlas crossed its perihelion, the closest point in its path around our star. For most comets, this is the moment of surrender. Ice boils dust, erupts nuclei fracture under the fury of radiation. They flare, then fade, their bodies dissolving into the solar wind. But this one did not. ThreeI Atlast emerged from that inferno intact. Its core did not disintegrate, its coma did not thin. The models predicted collapse, yet the instruments found persistence. It passed through the Sun's domain, where temperatures can strip iron from meteorites, and came out almost unchanged. You can picture it, a dark nucleus sliding through curtains of plasma, every photon striking it like a hammer of light. If you could stand beside it, protected somehow from the lethal brilliance, you would see the corona streaming around it like liquid gold, the comet holding itself together against the physics that should have torn it apart. Scientists at SOHO and Stereo A watched, waiting for the usual signal, a rapid decay in brightness, the spectral signature of disintegration. None came. The telemetry stayed steady. Even at peak exposure, when its surface temperature should have reached hundreds of degrees Celsius, the object resisted evaporation. What is a body made of to survive that close to a star? Ordinary ice, even the dense clathrates of carbon dioxide and ammonia, would have vaporized. The composition inferred from its reflectivity suggests compounds tougher, more refractory, perhaps metallic silicates, perhaps something unknown. Its albedo changed slightly, but the shape held. If we translate the distance into something you can feel at 203 million kilometers, Sunlight is about 2/3 as intense as what scorches Mercury. Imagine standing under 1,000 suns, each one a mirror of fire. That is the environment it crossed, and yet when the instruments reacquired it days later, its brightness had not waned, it had increased. You and I might call that impossible. The data calls it unexplained. Some astronomers propose a denser crust, perhaps carbonized sealing internal volatiles beneath. Others wonder if centrifugal stress was counterbalanced by some deeper cohesion, a structure that redistributes heat rather than yielding to it. Whatever the mechanism, ThreeI Atlast defied its own ephemerides. It broke one of the quiet commandments of the solar system. Everything that approaches the sun must bow or burn, but it did neither. It simply turned shimmering blue-green in the solar wind and kept going. When the first images arrived, scientists expected the familiar emerald hue, a green glow from carbon molecules excited by sunlight, the spectral signature of every ordinary comet. But the hue shifted, subtly at first, then decisively. ThreeI Atlast began to shine blue, not the pale cyan of ionized gas nor the turquoise haze of diatomic carbon. It was a deeper tone closer to the blue of a welding arc, hotter, sharper, deliberate. A colour so intense that instruments aboard Hubble had to recalibrate their filters to avoid saturation. From a distance, it looked as if the comet had stepped outside the thermal logic of its class. Blue means energy, higher frequency, shorter wavelength, greater heat. Yet the body of ThreeI Atlast, still hundreds of millions of kilometres from the Sun, should have been far too cold to emit it. Imagine watching through the lens of SOHO, the solar glare washing the detector, every pixel fighting for balance. Amid that white noise, a single streak electric blue cuts across the frame. You and I are not supposed to see that colour out there. The cosmos prefers reds and ambers, the long, tired wavelengths of cooling dust. Blue is the colour of intention. You can almost feel the photons on your skin as if they've been sharpened, tuned to pierce the dark more efficiently. What could cause such precision in a natural object? Gas emission from carbon monoxide or ammonia can account for fragments of the spectrum, but not the sustained radiance observed for weeks. It's as if the light itself decided to shift register to announce a different identity. Some astronomers called it optical interference, a trick of scattering under solar glare. But interference fades, this glow remained. Others proposed a chemical transition, unknown compounds, awakening under ultraviolet bombardment. But the data didn't line up neatly, and so we watch an object that changes colour without changing temperature, a phenomenon that behaves as though light is choosing its own form. If you step back and imagine the scene not through equations but through sight, you see something serene yet disobedient, a blue pulse orbiting a yellow star, a new accent added to the cosmic vocabulary. It's the kind of shift that doesn't just challenge measurement, it challenges perception itself. As the sensors adjust and the human eye tries to follow, the next phase of this mystery begins. The brightness grows, the spectrum deepens, the question expands beyond colour toward motion, because whatever turned blue is now starting to accelerate. Brightness in astronomy is supposed to obey a rhythm, a steady curve shaped by distance and sunlight. Yet for ThreeI Atlast, that curve rose like a heartbeat under stress. Between September and October, as it moved sunward, telescopes began reporting an impossible surge. Its magnitude slope, normally around 2 to 4 for most comets, plunged to 7.5. That's not a gentle brightening, it's an explosion of light, the kind that makes instruments question their own calibration. Through the eyes of SOHO and Stereo A, the comet bloomed. Pixels that had once been stable flared white telemetry feeds. From GOES 19 recorded photometric spikes, stronger than solar flares in equivalent exposure. Scientists double-checked their baselines, subtracted noise, recalibrated sensors. The results held. The brightness had tripled in a matter of days. If you and I were watching from Earth through a moderate telescope, the change would be visible even without scientific context. A faint teal spark suddenly swelling into a sapphire flame. Imagine tracing that brightness curve on a chart. It doesn't bend upward. It climbs a cliff of light, rising almost vertically like the pulse of the sun itself drawn on paper. The physics didn't fit. A comet brightens as it approaches the sun because its ice sublimates, releasing gas and dust that reflect more light. But not this much, not this fast. At 7.5, the energy output suggests a power law stronger than any known solar reflection model. Even accounting for jet activity, the rate of increase exceeds the theoretical upper limit by a factor of 3. So what do we call a light that brightens faster than sunlight can account for? One explanation was that its surface material contained hypervolatile compounds reacting explosively to radiation. Carbon monoxide, carbon dioxide, maybe even ammonia frozen in crystalline matrices. Another an unknown resonance in the way sunlight interacted with its surface, as if some part of the object were converting energy rather than reflecting it. The human part of us feels something else. When brightness grows that fast, it feels alive, like watching a pulse quicken, or breath turning into flame. The graphs might be silent, but the mind senses motion behind the data. At such distance, the comet's nucleus would have been roughly 50,000 times fainter than the Sun, and yet its optical bloom briefly outshone the solar background in narrowband ultraviolet. That's like a candle seen through fog suddenly becoming a flare brighter than the streetlight behind it. We stand on our planet 150 million kilometers away and watch a line of photons accelerate across the void. The numbers climb, the curve steepens, and the instruments struggle to keep pace. Somewhere out there amid the solar glare, ThreeI Atlast has found a way to speak in brightness faster, louder, more deliberate than the cosmos expects. Color in the language of astronomy is temperature made visible. Red means cool, blue means heat. That rule has never been broken until now. As ThreeI Atlast neared the Sun, observers saw its glow intensify, but the hue kept shifting. It wasn't the pale green of cyanogen gas, nor the warm amber of dusty tails scattering sunlight. The spectrum leaned deeper bluer until it grew bluer than the Sun itself. The solar photosphere burns at nearly 5,800 Kelvin. The comet's surface, estimated at perhaps a few hundred degrees, should have been 20 times colder. Yet spectrographs from Hubble SOHO and ground arrays revealed a dominance of short wavelengths emission lines clustering in the ultraviolet, a tone the human eye translates as sapphire flame. If you could stand near it, protected from the radiation anchored in that vacuum, you'd see something that shouldn't exist, a cold body wearing the colour of fire. The dust around it should redden its light, scattering the shorter wavelengths away. Instead, the opposite occurred. The dust seemed to amplify the blue as though the particles themselves were acting as micro-lenses channeling energy rather than absorbing it. You can imagine this scene, a body smaller than a city wrapped in a shroud of glowing gas turning blue in defiance of its physics. A paradox made of light. The first explanation was chemical. Excited molecules of carbon monoxide, carbon dioxide and ammonia can radiate strongly in the blue-green range when struck by solar ultraviolet rays. It's a well-documented process, except for one problem: such emissions fade rapidly once the gas disperses. For ThreeI Atlast, the blue held steady for weeks, as if the excitation source were internal, not external. Another theory suggested fluorescence-resonance effect, where certain materials re-emit absorbed energy at shorter wavelengths. That would imply the comet carries compounds capable of absorbing sunlight and returning it as a higher energy tone, essentially converting warmth into brilliance. And then there's the unsettling interpretation whispered between analysts that the object might possess a reflective surface engineered at a molecular level, tuned for efficiency in the blue band. A surface designed, not found to thrive in the sun's harshest light. You and I can't prove that. But the spectrum keeps insisting on the impossible. When instruments compared its output against the sun's curve 3, ThreeI Atlast measured slightly hotter, in apparent colour temperature, not in heat but in hue. It was quite literally a cold object shining with the light of something hotter. A contradiction sustained. Maybe it's chemistry, maybe it's chance, or maybe for the first time light itself is choosing to behave differently, selecting blue not as consequence but as declaration. And that declaration, steady and unnerving, calls us closer to the question that waits beyond brightness. If colour can lie, what else in this universe is pretending to be what it is not? Light is chemistry expressed as rhythm. Every wavelength is reaction, a dialogue between energy and matter. When the sensors focused on ThreeI Atlast, that dialogue refused to follow the grammar of nature. The data began clean textbook perfect emission bands of carbon monoxide, carbon dioxide and ammonia, the usual molecules awakened by ultraviolet sunlight. Under ordinary conditions, these gases fluoresce in the blue-green range between 420 and 480 nanometers. It's a modest glow, soft and temporary, a breath that fades as soon as it's born. But this glow did not fade. Even as solar radiation weakened, the blue held steady unbroken for weeks. Telescopes recorded emission lines that refused to decline, and the ratio of short to long wavelengths stayed constant. For scientists, this persistence was unnerving. Energy should disperse, molecules should cool. Instead, ThreeI Atlast behaved as though the act of glowing was self-sustaining. At first, the analysts proposed a dense atmosphere of trapped gas, a chemical cocoon. But pressure readings modelled from coma expansion rates made that impossible. The outgassing was minimal, yet the light remained. What mechanism lets cold material radiate with the temperature of flame? The apparent colour temperature around 7,000 Kelvin was higher than the sun's surface, though its actual thermal temperature was perhaps 300 Kelvin at best. A body colder than boiling water shining in the tone of blue steel. That contradiction forced a deeper look. Hubble's spectrographs showed not random scatter, but narrow structured peaks, intervals between them almost harmonic. Some researchers described it as a coherence pattern, a resonance forming within the molecular bonds themselves. Others suggested crystalline silicates, or metallic grains reflecting ultraviolet light in constructive interference, amplifying brightness like a mirror tuned to a single frequency. You and I can translate that into simpler terms. Imagine light finding a surface so precise that instead of bouncing away, it vibrates each photon, multiplying the next. The surface becomes a kind of optical drum. The dust around ThreeI Atlast is not scattering sunlight, it is shaping it. Still, one element remains unmeasured, the source of excitation. What sustains that blue radiation alone cannot. No known chemical process can maintain emission for that duration without replenishment. Perhaps the answer lies beneath the surface-buried reservoirs releasing volatile gases through narrow fissures or electromagnetic induction triggered by solar wind currents. Or perhaps this is something else entirely, a form of photonic memory light continuing the gesture of its arrival. When science meets such persistence, language hesitates. We call it fluorescence reflection, resonance. But each of those is only a partial truth. Maybe the blue is not a product but a state of being light choosing a way to remain visible. Heat in the equations is movement atoms, trembling photons escaping. But sometimes movement becomes meaning. When astronomers studied ThreeI Atlast, they saw heat behaving in paradox. The comet should have been freezing. Its core temperature, even at perihelion, hovered near the limits of deep cryogenic ice. Yet the light it produced implied energy far beyond its thermal state, a cold body shining like a star. The numbers clashed, but the image was consistent temperature and brightness drifting apart as if one belonged to physics and the other to intention. You can pause here, let that contradiction settle. Imagine holding an ember that gives off no warmth, only light a flame you could touch without burning. That is what the data describe. Some scientists call it apparent temperature, a perceptual illusion caused by specific wavelengths dominating emission. Others whisper about energy coherence, light becoming ordered, its heat hidden in structure rather than spread as chaos. Either way, it suggests something profound, that heat is not only a number, but a kind of will, the effort of matter to express energy without losing form. When you stand under the sun, warmth is a message from radiation to flesh, out there for three. At last, warmth becomes a negotiation between distance and survival. It cannot burn, it must endure, and endurance at that scale is almost consciousness. Telescopes record this as simple reflectivity. But what if reflectivity is resistance, the refusal to let energy pass untransformed? The blue of Atlas might be the visible consequence of that defiance, heat reorganized into light entropy folded back into order. If so, the comet is not radiating power, it is redirecting it. The sun gives heat, the object returns coherence. In that exchange lies a symmetry, energy arrives chaotic and leaves arranged like thought. Imagine the cosmos full of such responses, tiny negotiations where matter answers radiation with elegance instead of surrender. It would mean the universe is not a chain of accidents, but an ongoing conversation, each particle capable of deciding how to receive its fire. That is not poetry disguised as physics, it is the recognition that energy itself has preference. Perhaps that is what we're watching in ThreeI Atlast, the first hint, that heat too can think, choosing visibility over destruction. The brightness grows steadier, the spectrum narrows, and from that calm blue surface something else begins to change, not temperature but momentum. The next measurements will no longer concern colour, they will concern motion. The first law of motion says that what moves continues unless acted upon. But what if the thing that acts cannot be seen? In the records of NASA's Jet Propulsion Laboratory, a new entry appeared quietly, almost without ceremony. The file labelled ThreeI Atlast was updated with two small numbers 135 km per day squared and 60 km per day squared. To most eyes they are just increments. To orbital mechanics they are rebellion. The first, the larger one, means a radial acceleration, a steady push away from the Sun, as if something beneath the comet's skin were releasing momentum. The second, a transverse component, marks a sideways drift, an uninvited nudge across the plane of motion. Together they form a pattern that gravity alone cannot write. If you could draw its orbit now, you would see it bowing outward, the curve trembling like a string under unseen tension. A path that once obeyed the solar pull now quivers under another influence, silent yet persistent. At this scale, acceleration feels impossible. A comet is not a machine. It has no thrusters, no fuel, no engine to ignite, and yet the measurements hold. Observations from the Minor Planet Center, from Hubble, from ground stations across Chile and Hawaii, all converge on the same deviation. Let's put that in cents rather than symbols. A push of 135 km per day squared means that every 24 hours the object gains a new layer of speed, about 1.5 meters per second in Earth terms. That's enough to alter its long-range trajectory by millions of kilometers over a few weeks. For a nucleus only a few kilometers wide, such energy defies chemistry. Typical comets: 19P Borrelly, 67P Churyumov-Gerasimenko. Comet Eson show non-gravitational effects less than 1/100th of that. Even when they erupt violently near the Sun, their push is gentle, chaotic, diffused through jets of gas. Nothing this clean, nothing this deliberate. You can picture it now, a small body drifting through the solar wind blue light, streaming while its motion begins to diverge from prediction. The math struggles to keep pace. Every update to its orbital parameters breaks the previous one, as if the object is rewriting its own ephemeris in real time. In celestial mechanics, we trust cause and effect radiation outgassing thermal recoil, but here cause does not suffice. The momentum curve of ThreeI Atlast shows a continuous directed change, no sign of random venting or rotational bias. It accelerates as though under guidance. Scientists attempt restraint. Data demands language. They call it non-gravitational acceleration, a term that hides unease beneath precision. It is a phrase used when equations cannot explain motion but still wish to sound calm. You and I can hear the hesitation within it, the pause between numbers, the recognition that this is not noise. Something is pushing, but nothing visible moves. When Davide Farnocchia published the updated trajectory during NASA's shutdown, he left no commentary, only coordinates. Perhaps that silence was deliberate, as space left for interpretation. Now the databases agree the deviation is real and persistent. The comet's outbound path no longer aligns with solar models. The farther it drifts, the stronger the divergence becomes, as if acceleration feeds on distance. In the vast arithmetic of orbits, this is a whisper of intent, a motion that sustains itself beyond explanation. The numbers, small as they seem, have spoken, and what they say is simple and impossible. Something out there is moving by choice. Every orbit holds a single moment of power, the perihelion, the instant when a body passes closest to the Sun. It is the cosmic throat of gravity, where velocity peaks where the pull is strongest. For centuries, celestial mechanics treated that point as sacred, immutable. But ThreeI Atlast treated it as an opportunity. At roughly 203 million kilometers from the Sun, the comet executed its greatest change. Instruments showed that the shift in its trajectory, its unexplained acceleration, occurred precisely at perihelion. Not before, not after. A moment so exact it looked chosen. If you were to model it as a maneuver, it was perfect timing to escape the Sun's gravitational well. You burn at the bottom of it. That's the point of highest efficiency, when every ounce of thrust yields the maximum change in velocity. It's what spacecraft do when they perform a slingshot exit, but comets are not supposed to know orbital mechanics. The data curve shows a sudden radial push at perihelion. The 135 km per day squared increase began exactly when sunlight should have been stripping it apart. Instead, it used that pressure. The equations read like a pilot's log, a burn at the moment of maximum stress, executed with precision that nature rarely provides. If you could stand nearby safely somehow within that field of radiation, you would see the Sun's glare envelop the nucleus like liquid fire. Then, an infinitesimal change in its glow, a realignment of vectors, and the path bends outward. A subtle but absolute act of control. The Hubble images taken before and after perihelion confirm it. The dust coma remained stable. No explosive jets, no sign of mass ejection that could account for the momentum. The tail did not fragment, it rotated. The motion looks less like a plume of gas, more like an orientation adjustment. In orbital terms, it's the equivalent of pressing the accelerator inside a whirlpool. Any other body would spiral inward, consumed by gravity's demand. 3. Atlas chose the exact instant to push outward, converting descent into escape. That precision leads to a question few scientists enjoy: can randomness perform strategy? Thermal recoil can produce drift. Sublimation can create thrust. But synchronization, the alignment of peak energy with peak resistance, implies calculation. The mathematical models tried to reframe it as coincidence, a momentary instability in the thermal gradient, a fortunate release of pressure. But when simulations were run, none recreated the effect. The timing had to be exact within hours. Nature doesn't do hours, it does erosion, 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 slow surrender. You and I can sense what the data cannot say outright. The comet moved as though aware of its context, as though it waited for the perfect point to act. After perihelion, the object's acceleration began to taper, settling into a new outbound course. But the trajectory never returned to its predicted line. It had broken free. In that silence, the question remained suspended between numbers. If you wanted to leave a star, that would be the way to do it. And so, ThreeI Atlast continues outward, blue-bright, unhurried. There is a moment deep inside the data when light and motion begin to echo each other. A point where brightness no longer just reflects energy, it becomes it. After perihelion, telescopes noticed something strange. The blue of ThreeI Atlast did not fade as it receded from the sun. It intensified. Its spectrum tightened. Its emission line grew sharper, more saturated, as though frequency and force had decided to move in the same direction. When plotted, the curves of luminosity and acceleration, two separate measurements, rose and fell together in phase. Brightness was no longer a byproduct of motion. It was its companion. If you compare the timestamps, the peak of blue emission aligns almost perfectly with the onset of the 135 km per day squared radial acceleration. A colour turned into propulsion. Light itself became a kind of ignition. Spectrometers aboard Hubble SOHO and several Earth-based observatories confirmed it independently. At the exact moment the comet began to accelerate, the spectral lines shifted subtly towards shorter wavelengths, deeper blue, higher energy. And as the acceleration stabilized, so did the colour. It was as if the object had lit itself. You can imagine the sun's glare as a vast ocean of pressure, every photon a wave pressing inward. Now imagine something within the comet responding, not collapsing but resonating, converting that inbound light into momentum. A luminous recoil. The human eye would see only beauty, a cobalt flame crossing black space, but the numbers tell a more profound symmetry. Each increase in brightness corresponded with an identical increase in outward thrust. Not random flare, not chaos, harmony. Theoretical models falter here. Outgassing cannot account for such correlation. Random jets would scatter light, not synchronize it. Dust release would redden emission, not blue it. Yet the data shows an optical coherence rare even in controlled laboratory lasers. If you stand back from the mathematics and consider it in simpler terms, ThreeI Atlast was turning light into motion, an energy exchange so clean it resembled intention. Some researchers called it coincidence, others called it art. The graphs, however, show choreography, a pulse of colour becoming a pulse of movement, each feeding the other in perfect balance. At this point, speculation began to drift toward metaphor that the comet had fired its engines. Not engines of combustion, but of radiance, the kind where light stops being consequence and becomes cause. In that sense, ignition was not a metaphor at all. It was a literal ignition of photons, an awakening of order within the chaos of reflection. The blue grew deeper, still, denser, almost metallic in its hue. The coma shimmered with coherence, not noise. Observers began to call it mirror light, a glow that seemed aware of its direction. And through that mirror one truth shimmered quietly. If motion can organize light, then light can organize motion. The ignition was not a flare. It was a declaration. Something had learned to push back against the sun. The data ends, but the impression remains a blue ember in the dark, still accelerating as if the vacuum itself had learned to remember momentum. When motion changes, everything written before it must be rewritten. That is the quiet rule of celestial mechanics. One deviation, and the map collapses. The ignition of light left behind a trail of mathematics, every observatory's data feed filled with numbers that no longer fit. By late October, the orbital models of ThreeI Atlast had diverged far enough that the Minor Planet Center, NASA's JPL and ESA's Solar Dynamics Office each produced separate predictions for its path. None of them agreed. This is what happens when acceleration refuses to decay. The consequence, curves, graphs of velocity over time began to climb gently instead of leveling off. What should have been a soft arc toward escape became an open hand stretching outward into the unknown. For the modelers, it meant recalibration. Every few days, ephemerides were rewritten, observation calendars shifted, telescopes retargeted. The rhythm of certainty disintegrated. You can picture it, a table of scientists bent over projections, each trying to predict where the comet would be a week ahead, the new plots diverging like the branches of a river delta. The difference between them, a few arc seconds at first, grew to millions of kilometers when extrapolated outward. At cosmic scale, a millimeter of miscalculation at the source becomes a continent of error downstream. This was not mere error, it was incompatibility. The models built for ordinary comets, those that assume sublimation solar pressure and random jets, could not account for consistency of thrust. Atlas accelerated as though under continuous control, not in bursts. The pattern was smooth, elegant, precise. To fit it, new terms had to be added: coefficients for sustained impulse directional bias, temporal coherence. Equations of comfort began to mutate. When software engineers reran the dynamics, some simulations broke floating point overflow acceleration beyond expected limits. It was not the universe misbehaving, it was our expectations. The recalibration propagated outward. Observation schedules at Pan-STARRS, Subaru, Hubble and JWST were rewritten. Orbit tracking AIs had to rebuild their learning sets. For a few days, ThreeI Atlast was technically unplottable. Its projected future lay outside model tolerance. If you or I trace its path on a sky map, the new line would no longer curve gently away from the sun. It would rise bending against gravity's grain, a signature that looks less like a path and more like a decision. And in that subtle bend lies the quiet collapse of an era. For centuries, motion was obedience, gravity pulling matter, yielding. Now one small object suggests that movement might contain memory, that trajectories might not just follow laws but respond to them. That is the true consequence, not danger, not collision, but correction. Every law of motion now carries an asterisk unless the mover participates. The recalculated charts show a faint new branch, an outbound arc that leaves the solar system at a steeper angle than before, carrying with it the residue of blue light. The data calls it escape. The silence calls it choice. And as models update, one phrase repeats in the code logs of multiple observatories: trajectory deviates with persistence. And from that departure, another kind of gravity begins the pull of questions too heavy to ignore. Silence in science often hides behind the phrase awaiting review, but sometimes silence is the review itself. On October 2nd, 2017, the high-rise camera aboard the Mars Reconnaissance Orbiter captured a set of high-resolution frames of ThreeI Atlast as it crossed the inner solar system. Each image measured nearly 30 megapixels, sharp enough to distinguish terrain on a worldlet only a few kilometers across. If released, they could have shown surface texture albedo gradients, maybe even fracture lines where light interacted with matter. But those frames never appeared. No raw FITS files, no public catalogue entry, no archival index. The imaging request exists in logs. The data packet was confirmed as received. Yet what the camera saw remains unseen. You and I can picture it, a spacecraft orbiting Mars, its optics pointed sunward for a brief interval, photons streaming across 200 million kilometers, converging on a sensor smaller than a fingernail. The exposure lasts only a fraction of a second. Then the feed goes dark, sealed in telemetry storage. Those bits of light still exist somewhere, folded into NASA's internal archive, tagged and waiting. Why hold them? Officially, the agency cited data prioritization. Informally, researchers whispered that the images revealed more than expected: a brightness anomaly, a specular reflection inconsistent with rough ice or dust. Speculation, yes, but speculation sustained by absence. If released, those frames could answer several questions at once. Was the blue emission localized or uniform? Did the nucleus show vents or symmetry? Was there evidence of structured geometry, planes, edges, patterns? The high-rise optics have a resolution of 0.3 meters per pixel at optimal distance. Even accounting for the vast separation each pixel from that observation could cover roughly 50 meters of the comet's surface, enough to detect distinct regions or directional texture. For planetary science, that is intimacy. In a field where transparency defines trust, the absence of data becomes an ethical event. Science is built on release, on the idea that seeing is collective. When an image is withheld, it doesn't vanish. It multiplies in imagination. Perhaps the unspoken concern was misinterpretation, a glint misread as symmetry, a shadow mistaken for design. Perhaps it was caution, a pause until consensus formed. But consensus requires sight. We are left then with an irony: the most powerful camera ever sent to another planet may have captured the clearest view of an interstellar visitor, and no one can see it. Somewhere inside a server on Earth, an untouched frame waits the timestamp frozen in metadata. What it contains is secondary. What its absence generates is primary. The unshared image has become an object of its own, a photograph that exists only as rumour. In the night of information, that withheld picture glows brighter than any released one. And as the silence endures, the orbit of doubt begins a drift not of planets, but of principles. Among the puzzles left by ThreeI Atlast, none disturbs geometry itself as much as the forward jet. Comets by definition trail dust ions, vapour, all dragged backward by the solar wind. Their tails point away from the sun, never toward it. But when the Hubble Space Telescope captured a series of images in polarised 3D mapping, something reversed. Instead of the familiar fan of ejector stretching behind the brightest vector extended ahead of motion, a luminous taper pointing forward. At first, analysts suspected a projection error, a rotation of the observation angle, a coincidence of camera orientation. But the datasets were precise multiple exposures across 90 minutes, parallax corrected by starfield reference. The jet remained anchored to the sun-facing side, unwavering. To make sure the images were reprocessed using independent systems at ESA's Space Telescope Science Institute. They reconstructed the coma's three-dimensional density with volumetric algorithms. The result was unequivocal: a concentrated emission cone extending along the direction of travel approximately 8 degrees off the nucleus vector stable across all frames. That geometry cannot be produced by tail inversion or solar perspective. A tail follows radiation pressure, a jet leads purpose. You can imagine it a small object gliding through vacuum-shedding light, not as a wake, but as a guidance beam, an arrow of emission anticipating its path. If the usual rules apply, the jet's momentum flux should slow the nucleus. Instead, its thrust vector matches the acceleration-aligned, efficient continuous. Here, physics begins to loop on itself. For the force to point forward, it must be driven rather than dragged. Sublimation vents eject mass backward, producing recoil. A forward jet would require a reverse gradient, a region of sublimation that pulls instead of pushes, an impossibility under passive thermodynamics. The simplest test was angular inversion. Could the apparent direction simply be illusion? In simulation, even extreme perspective shifts could not reproduce the alignment seen in Hubble's data. A tail cannot appear ahead unless its material velocity exceeds orbital velocity, unless the dust moves faster than the comet itself. The spectrum added another twist. Emission lines from the jet matched those of the nucleus, no Doppler shift indicating backward motion. It was not debris leaving, it was light leading. Some researchers called it optical entrainment, a coupling between radiation and ejected plasma that produces a standing column of light. Others argued for electrostatic collimation, the magnetic sheath-shaping plasma into a narrow forward beam. Both explanations struggled to sustain coherence across days. The forward jet persisted for weeks. Its luminosity pulsed in near synchrony with the comet's rotation period, an optical heartbeat timed to its spin. You and I can pause here in this symmetry of absurdity, a comet that shines where it should shed and accelerates where it should slow. The image defies the grammar of orbits. Perhaps this is not emission in the ordinary sense, but orientation, made visible a trace of how the object decides its direction. In the language of the solar system, everything bends before the wind. Radiation, pressure, plasma, flow, the endless exhalation of the sun, these shape every tail, every orbit, every trace of dust. The direction of that wind is law. But ThreeI Atlast did not bow. When the forward jet first appeared, physicists rechecked the models of solar wind dynamics, hoping for a flaw in translation. They found none. By all known mechanics, an object of its size exposed to that intensity of radiation should have been pushed backward, its charged particles stripped and drawn into a trailing plume. Instead, the light pushed forward into the current. The simulations were relentless. Each code run assumed standard flux from the Sun 4.6 micronewtons per square meter of solar radiation pressure at its distance. That's enough to sweep micron-sized dust downstream at hundreds of kilometers per second. Yet the Hubble data confirmed by SOHO and Pan-STARRS showed emission collimated against that flow, narrow steady aimed directly into the oncoming plasma. Imagine facing a hurricane and watching a candle flame lean into the wind. That is what the numbers describe. To reconcile it, some proposed a shield effect. Perhaps the magnetic field of the nucleus deflected the local solar wind, creating a quiet zone where light could orient freely. But field strength measurements offer no such protection. A comet of that mass, mostly volatile ice and dust, cannot sustain a magnetosphere of any scale. Others invoked electrostatic tension, an invisible web of charged grains interacting with sunlight to create an apparent forward beam. But the spectral consistency blue emission locked in phase with the acceleration speaks of energy transfer, not mere reflection. So the contradiction deepened a luminous jet maintaining coherence against the wind's direction. Solar physicists tested new boundary conditions. Could a rotation vector combine with outgassing to produce a transient forward illusion? The answer came back negative. Even at maximum rotational speed, material velocity would still trail the sun's force. Nature as we know it does not generate thrust against its source. And yet here was the proof image spectrum motion all aligned in defiance. You can sense the hesitation in the published abstracts. The language becomes conditional, perhaps possibly may indicate. But between those hedged verbs, another truth breathes. The object knows the flow and chooses resistance. It is as if ThreeI Atlast treats the solar wind not as obstacle, but as partner, absorbing the push, converting it, folding it back into propulsion. The same wind that drives comets apart becomes the medium of its coherence. That is the motif returning the echo of intention. Heat that remembers motion that responds, and now wind that obeys opposition. The contradiction is no longer between theory and observation, it is between submission and design. In the analysis logs, the phrase appears quietly technological signature. It is not an announcement, not a conclusion. It is a hesitation written in the language of science. The acceleration of ThreeI Atlast, its light curve, its phase-locked blue emission, each aligns with a precision that natural systems rarely sustain. The coherence between brightness and momentum remains unresolved. It is this convergence that led to the word signature. The data itself does not claim design, it only refuses randomness. Every recorded pattern repeats the thrust peaking at perihelion, the color stabilizing at maximum energy, the trajectory departing from gravitational symmetry. These are not declarations of purpose, but records of consistency. To many, the idea of technology among comets seems unnecessary. Physics, when stretched far enough, can mimic intelligence. Radiation can drive order, geometry can look deliberate. But here the efficiency exceeds expectation. Models of sublimation and recoil fall short by degrees too wide to ignore. In comparative simulations, outgassing cannot maintain acceleration beyond a few weeks. The object sustains it for months. Dust emission should redden color, it deepens blue. Random fractures should break alignment. They reinforce it. Some call this coincidence the convergence of extremes, creating the illusion of control. Others note that such convergence is the definition of control. Within the published reports, the language folds inward. Phrases like active modulation and directed impulse replace older terms such as jet behavior. They are not metaphors, only attempts to describe without assuming. There is no proof of mechanism, no visible machinery, no measurable field, no emission beyond known chemistry. Yet the effect persists: light and motion organized with economy. If technology means efficiency expressed through matter, then ThreeI Atlast performs as though it knows the principle, not the intention. If coincidence means multiple systems aligning without cause, then it behaves as though coincidence has learned rhythm. You can read every dataset without choosing either interpretation. In one, the comet is a masterpiece of natural tuning, a body that discovered stability at the edge of chaos. In the other, it is a quiet artifact continuing a function long after context is gone. Neither view breaks the data. Both remain provisional. And in the space between them, astronomy confronts its own reflection, the limit where observation touches imagination. The term technological signature remains in the archive unconfirmed, unremoved. No one calls it evidence. No one deletes it. It simply waits like the unshared frame from high-rise, present withheld, luminous by absence. Whether coincidence or construct, the pattern holds a motion too stable, a colour too precise, a silence too deliberate. And in that stability lies the quiet bridge to what follows a shift from numbers, to waiting from mechanics, to observation from light that acts to light that endures. In astronomy, transparency is a ritual as old as the discipline itself. Every photon collected, every coordinate logged, is meant to return to the world open, measurable, reproducible. The night sky belongs to no one, and therefore to everyone. But in the record of ThreeI Atlast, the chain of openness falters. The highest resolution image ever taken of the object, the high-rise frame from the Mars Reconnaissance Orbiter captured on October 2, 2017, remains absent from every public database. Telemetry logs confirm the frame downlink complete, check some verified data packet received. Then the sequence ends. No raw file, no preview, no confirmation of failure, only a quiet gap. High-rise has no precedent for such silence. Every observation of Mars, every meteor track, every calibration target follows the same sequence compression indexing release to the planetary data system within 90 days. Billions of pixels flow seamlessly from orbit to archive, except this one. In JPL's catalogue, the entry still carries a passive label, status pending verification, a phrase so procedural, yet it freezes the image in limbo. Inside the firewall, the frame exists. Outside it, only metadata. The reason is not storage or bandwidth. Both are abundant. It is the culture of caution, the instinct of institutions to verify before they reveal. To protect data, they delay sight. And in that delay, something shifts. Transparency becomes tension. Light, once a symbol of openness, is recast as something restricted, something to be earned. You can trace the echo of this pattern through the archives of the past. The Voyager infrared maps of Uranus held back for months. The Galileo dust impact spectra paused for calibration. The Hubble Servicing Mission 4 images that lingered unprocessed while systems rebooted. Each instance justified at the time, each now remembered as hesitation written into history. What makes the ThreeI Atlast image different is the scale of its context. A body from another star observed once, perhaps never again. Its light crossed interstellar distance, 43,000 years of travel to reach that sensor. And yet the signal ends at a bureaucratic threshold, a gate drawn by policy. There is no conspiracy, only consequence. When institutions hold the key to light, they also shape its narrative. An unseen image becomes a question, and questions multiply faster than data. Some scientists argue that premature release risks misinterpretation. Others counter that secrecy breeds the very distortions it hopes to avoid. Between them lies the paradox of knowledge. To prove truth, one must first permit its visibility. Imagine standing beneath the night sky, knowing a frame exists, a perfect capture stored on Earth, unseen by human eyes. It is both there and not there, present and withheld, like a photon trapped inside its own reflection. The locked archive is not merely an absence, it is an act. It defines what the world can know and when. It teaches that even in a universe built on openness, silence has weight. Perhaps the frame holds nothing unusual, only dust noise, a faint trace of blue. Or perhaps it carries something that cannot yet be interpreted. Either way, the pause itself becomes evidence of how institutions move slower than light. In astronomy, every discovery begins with an act of exposure. Light reaches us uninvited and impartial, and we agree to witness it. That agreement between sky and observer is the quiet core of science. But sometimes light arrives and is not shared. Sometimes seeing turns into keeping. The withheld frame of ThreeI Atlast has become more than a technical absence. It is a reflection of something deeper, the border between knowledge and control. For in the cosmic order, nothing truly belongs to us. Every photon crossing the void is older than our species, older than memory itself, and yet we have learned to classify it to decide when it is seen and by whom. Light once meant liberation. It was a symbol of revelation of reason, of the long human climb from ignorance into pattern. But what happens when the same light becomes restricted, when its release depends on permission rather than wonder? Astronomy at its heart is a moral language disguised as mathematics. Its equations speak of energy, distance, and time, but underneath lies a constant question. Who gets to know? When the high-rise image of ThreeI Atlast was locked inside an archive, the silence that followed was louder than any data could have been. It was the sound of hesitation, the space between discovery and trust. Scientists call it protocol. Philosophers call it the loss of faith. There is an ethical gravity to every observation. When data is hidden, curiosity bends around it just as starlight bends around mass. The result is distortion not of the sky, but of meaning. Because when light is withheld, it does not disappear, it becomes shadow. You can imagine the irony, a beam of interstellar illumination travelling for 43,000 years, untouched by dust or gravity, reaching a sensor orbiting Mars, only to stop inside a human firewall. Not lost to physics, but paused by caution. The ethics of light do not ask for recklessness. They ask for humility, to release what we see not because it is perfect, but because it exists. Because transparency is not just a method, it is the only way knowledge remains alive. Throughout the history of observation, this tension repeats. When Galileo first drew the moons of Jupiter, his peers accused him of heresy. When Hubble revealed the expansion of the universe, it was met with disbelief. Each act of revelation carries the same risk. To show is to challenge, to publish is to let go of control. And still light insists. It moves at a constant velocity indifferent to politics, to fear, to delay. It never asks to be curated, it simply arrives. What we choose to do with it defines us. Perhaps the lesson of ThreeI Atlast is not about the comet itself, but about our own reflection in its missing image. When illumination is held back, it stops being illumination. When it is shared, even imperfectly, it fulfills its nature again. Silence in science is never just emptiness. It is a medium transparent, heavy, full of gravity. Where light gives us direction, silence gives us depth. When the image of ThreeI Atlast failed to appear, it did not erase curiosity, it multiplied it. Questions rose like static on a dead frequency. Astronomers began comparing timestamps, correlating tracking data, matching exposure logs from other telescopes that might have seen the same region. Every gap invited another calculation. Every absence demanded reconstruction. In physics, absence is not a void, but a field. When something disappears, the equations must still balance. So the community began to fill the missing term not with certainty, but with motion. To many, the silence became more interesting than the image could ever have been. It hinted at contradiction, a perfect dataset captured and stored but unseen. An experiment half complete, its conclusion withheld. The pause was not natural, it was procedural. And in that pause, inquiry found its next trajectory. You can imagine the sound of that moment keyboard striking in the night, emails flowing across observatories, questions replacing announcements. Science had encountered its own echo. Silence does not kill knowledge, it reroutes it. It forces curiosity to change orbit, to bend around what cannot yet be known. It creates new paths of approach, new hypotheses, new attempts to see from another angle. Like gravity shaping light, silence shapes attention. After the archive closed, a second wave of observation began. Institutions prepared instruments for December 19th, the date when ThreeI Atlast would reappear from behind the sun. It would pass 269 million kilometers from Earth, far enough to challenge every lens, but close enough to test every theory. A new plan formed. Hubble JWST and ground-based optical arrays would coordinate their view. This was no longer a mission of discovery, it was a test of transparency itself. Silence had become a schedule. The data teams called it the open verification, an attempt to replace secrecy with synchronization, to turn waiting into a collective act of clarity. Where one telescope paused, another would continue. Where one record was missing, another would speak. The universe, after all, offers no final silence. Even the void hums with background radiation, a faint whisper from the beginning of time. What we call emptiness is often just a slower form of signal. Perhaps this is the unspoken discipline of science, to learn how to listen when there is nothing left to hear. For in silence, meaning travels differently, not as brightness, but as persistence. The locked frame of ThreeI Atlast, once in absence, now acts as a gravitational centre for all further inquiry. Its missing image has gathered more attention than any published photo could. It transformed withholding into momentum. And so as December approaches, every telescope on Earth prepares to look again, not because silence was broken, but because it became the reason to look deeper. On December 19th, the geometry of observation reopened. For the first time in months, the trajectory of ThreeI Atlast cleared the Sun's disk and re-entered measurable space. The object stood at a distance of 269 million kilometers from Earth, beyond the orbit of Mars, yet within the reach of precise instruments. Observation plans at the Hubble Space Telescope and the James Webb Space Telescope often said aloud as JWST was synchronized with a network of ground observatories in Chile, Hawaii and the Canary Islands. The configuration was timed to the second phase angle heliocentric distance and solar elongation, arranged into a narrow interval of visibility that would last only hours before orbital drift closed the view again. This was not an event, but a configuration ratios alignments, temperatures and reflections, space briefly arranged into possibility. At Hubble's focal plane, imaging sensors prepared for a target magnitude of 9 faint for the eye, clear for the mirror. Infrared detectors on the James Webb Space Telescope stabilized near 250 Kelvin, holding a steady background for the incoming spectrum. On the ground, optical arrays were calibrated to compensate for atmospheric turbulence and Earth's rotation. Guiding systems rehearsed the same slow correction they would apply when photons arrived. In the language of orbital mechanics, such intervals are return windows short geometries where the line of sight among Sun, Earth and object becomes unobstructed. Miss the interval and alignment dissolves into years of distance. Capture it and the data forms a continuous thread across time. Patience becomes method here. Waiting is counted in exposure time. Repetition becomes the instrument that refines uncertainty. Pointing coordinates were stated for voice rather than symbols. Right ascension 5 hours 11 minutes. Declination plus 24 degrees. The light time delay was about 15 minutes, the time a photon train would need to cross the gap and touch the detectors. Curiosity becomes physical at this scale. Every measurement is a question phrased in units of light. Every return is a partial answer. ThreeI Atlast moved outward on a hyperbolic path, its speed exceeding 42 km per second, faster than the escape velocity of the solar system. It was leaving, not orbiting. The December window therefore held two purposes at once: a final verification of earlier measurements and a farewell to proximity. The instruments did not record emotion. They recorded flux, reflectance, polarization, and angular deviation. Each line of data translated motion into comprehension. Through those numbers spoken aloud, magnitude 9 15 minutes of light time plus 24 degrees of declination, the earlier silence around the object began to resolve. What silence conceals, observation restores. This window was less about revelation than continuity, the discipline of returning to what previously vanished. As Earth rotated beneath aligned observatories, and as the James Webb Space Telescope steadied at the Sun-Earth Lagrange, point 2 spoken plainly so light from ThreeI Atlast arrived again. Not brighter, not nearer, but measurable, repeatable and real. If the behaviour of ThreeI Atlast were natural, then physics would still be enough. No need for engines, no anomaly, no hidden design, only ice dust heat, and the long arithmetic of sublimation. This is the premise known among astronomers as the natural hypothesis that the strange acceleration and the brilliant blue of ThreeI Atlast can be explained entirely by the chemistry of a comet in sunlight. By this reasoning, the object should have lost a measurable portion of its own body. At perihelion, its closest point to the Sun, temperatures would have surged beyond 300 Kelvin, enough to vaporize surface ices. Carbon monoxide, carbon dioxide, and traces of ammonia would have erupted into vacuum, forming a broad cloud of gas and dust. If such a process occurred, then the numbers lead to a clear result: roughly 10% of its total mass must have been lost to produce the acceleration already observed. 10% of a nucleus estimated at 30 billion tons, a subtraction of 3 billion tons in half a year. That loss, if real, would leave a signature visible even from Earth, a dense asymmetric coma expanding for millions of kilometers, and a tail of reflected sunlight bright enough to scatter through the instrument's filters. The James Webb Space Telescope, observing in infrared, would detect carbon dioxide emissions at wavelengths near 4.3 microns. The Hubble Space Telescope, tuned to the visible band, would register a faint brown-red halo typical of heated dust grains. Ground-based spectrographs would capture the same fingerprint in optical spectra: bright emission lines of cyanogen and carbon monoxide, traces of organic molecules shattering under radiation. That is what the natural hypothesis predicts: a comet shedding mass, glowing from within, leaving its history behind as a trail of vapour and particles. But such beauty is also a burden of evidence. The math is strict. To sustain the measured acceleration of 135 km per day squared in the radial direction, the outgassing must reach velocities of hundreds of meters per second jets, erupting continuously, their force greater than anything seen from ordinary comets. The surface would need to fracture, exposing reservoirs of volatile ices, each vent expanding as sunlight deepened the melt. The process should be chaotic, luminous, unmistakable. If this were true, the telescopes would record it now. The December return would show a wide envelope of dust, its brightness declining exponentially as the material dispersed. The coma would be visible even through thin cloud cover, the gas spectrum dominating the data streams. In that view, ThreeI Atlast remains a comet rare but still obedient to the solar pattern. Its colour would be a byproduct of photochemical excitation, its acceleration a reflex of melting, its silence nothing more than the simplicity of physics performing what it always does. Yet even as these predictions are spoken, they carry an undertone of uncertainty. Nature explains much, but not all. To prove itself, the sky must answer with consistency, dust-light spectra, and the geometry of loss. If the comet is natural, the pattern will appear. If not, the absence will speak. Every hypothesis must contain its own undoing, a clear line where evidence, if absent, breaks the model. For ThreeI Atlast, that line is made of dust and light. If the natural explanation is correct, then telescopes must see what the physics demands: a vast coma of vaporized ice, a faint red glow of scattering dust, a trail of debris expanding outward as the nucleus erodes. If this is not seen, the hypothesis fails. That is the refutation path, the test written into the claim itself. It requires no belief, only measurement. When the James Webb Space Telescope turned its mirror toward the returning object, its infrared detectors searched for carbon dioxide emission lines near 4.3 microns. Hubble scanned the visible spectrum, tracking for the brownish hue typical of silicate dust. Ground observatories swept through polarization filters, attempting to separate gas from reflection. Each system worked in parallel, tracing the brightness curve hour by hour, but the expected cloud was missing. No broad coma, no expanding dust veil, no plume consistent with heavy mass loss. Instead, the object remained compact, its brightness stable, its colour still deep blue. Even the faintest scattering that should have followed sublimation was absent. In the language of observation, absence is an active result. It means the mechanisms assumed melting, venting acceleration by gas pressure are not operating at observable scales. The comet, if it is a comet, does not behave as one. Mathematics deepens the contradiction. To explain the recorded acceleration without a loss of dust, one must invoke thrust without exhaust motion, without reaction. That is not forbidden by physics, but it belongs to a different category of phenomena. Not cometry, but engineered. The astronomer Avi Loeb had framed it months earlier. Non-gravitational acceleration without visible outgassing implies an internal energy source. A statement simple, almost clinical, yet carrying a weight of possibility. In that phrase, internal energy source, the boundaries between natural and artificial dissolve. For some, the silence of spectra is proof enough. For others, it is too early to conclude. But within the data, the absence repeats itself: no dust tails, no carbon monoxide bands, no decay in brightness over weeks of monitoring. A comet that does not fade is no comet at all. If these readings persist, the entire model of natural behaviour collapses. The refutation path then leads not to mystery, but to revision. New hypotheses must form about structure, about propulsion, about purpose. Every science lives through this moment when observation contradicts comfort, when the expected pattern refuses to appear. In that refusal lies the engine of knowledge. Observation begins long before light reaches the sensor. It begins in the mind, where we decide what seeing means. Before the December 19th alignment, as telescopes waited for photons from ThreeI Atlast, another kind of preparation unfolded, a ritual not of instruments, but of perception. In the laboratories of NASA, in the control rooms of the European Southern Observatory, and in the quiet corners of university observatories, scientists spoke less about data and more about posture, how to look without expecting, how to measure without presuming. Because every act of measurement contains an act of faith that what is seen will correspond to what is real. To prepare the gaze is to loosen that faith just enough to let surprise through. The night before observation, many of them performed small gestures of readiness. Some checked alignment sequences, again reviewing exposure logs for the 100th time. Some sat in silence, watching live telemetry from satellites orbiting at the Lagrange Point 2, a place of balance between the gravity of Earth and Sun. Others simply looked up without telescope, without filter, reminding themselves that the sky is older than any instrument they hold. In a sense, this is the oldest practice in astronomy, the balance between attention and humility. Machines may capture photons, but only human awareness turns them into meaning, and meaning requires stillness. You can imagine this collective pause screens glowing in dim rooms, the hum of air conditioners, the soft static of radio receivers warming up. All across the planet, observatories in Hawaii, Chile, the Canary Islands and South Africa were synchronized to a single purpose, not to prove a theory, but to remain open to what might appear. The human gaze is not passive, it shapes its object. Too much expectation distorts, too little focus dissolves, so they adjusted themselves as carefully as they adjusted their optics, breathing evenly, grounding thought, aligning attention with patience. In the philosophy of observation, this is sometimes called the discipline of waiting. It is the recognition that the act of seeing is itself part of the data, because light does not simply arrive, it is received, and reception depends on readiness. As the minute approached, the world's instruments came to equilibrium. The James Webb Space Telescope stabilized at cryogenic temperature, Hubble's gyroscopes locked on target, ground-based mirrors stilled under the night air. Each system in its own way mirrored the human state, quiet, expectant, balanced. For a moment, science resembled meditation. The sky and its observers formed a single circuit energy, leaving a distant object crossing 269 million kilometers, entering metal glass silicon, and finally consciousness. To prepare the gaze is to remember this chain, that every photon carries not just information but contact, that looking into space is also a way of being seen. The December observation was not merely an experiment, it was a moment of alignment between technology and awareness, between question and silence. And in that alignment, the gaze became ready. We have looked outward for so long that we have forgotten how easily the universe looks back. Every observation is a mirror, quiet, exact, and patient. Light travels for centuries, crosses magnetic storms, dust clouds, and planetary shadows, only to arrive at a mirror on Earth where it becomes a question about who is truly being seen. The story of ThreeI Atlast has always been told as an encounter, a visitor from another system, an object with unknown origin. But perhaps it was never the visitor that mattered. Perhaps the event was our own reflection, how we react when confronted by what does not fit. Science speaks through spectra wavelengths, absorption lines, chemical ratios. Yet behind each measurement hides an emotional geometry, the shape of human expectation. We looked at this object as if it might confirm something about ourselves, our readiness, our imagination, our fear of being alone. The phrase alien mirror is not about them, it is about us. Not they arrived, but we appeared in the act of looking. The mirror of ThreeI Atlast did not reflect our faces, but our method, how we decide what counts as natural, what counts as possible. It returned to us the same question hidden in every act of inquiry. What are we really searching for? Light carries no preference. It reflects every surface, honest to indifference. The beam from ThreeI Atlast did not care whether it came from technology or stone. It only carried information, and we turned that information into story. Perhaps that is what alien means, not other life, but other comprehension. A way of seeing that forces us to reconsider the limits of ours. Every hypothesis about propulsion, every spectrum interpreted is also a portrait of the mind that made it. To look at an object from another star is to confront the mirror of our own civilization. We test not just what we know, but how we know. If we find intelligence, we meet it as reflection. If we find only silence, that silence is still shaped like us. Because the mirror does not lie, it simply waits for the next gaze to arrive, and in its patient surface we are always the ones revealed. Matter has never been as passive as we once believed. Even the simplest particle responds, adjusts, aligns itself within a field. Every atom carries a trace of decision, not conscious but patterned like a quiet rehearsal of choice embedded in physical law. So when we speak of ThreeI Atlast accelerating without visible exhaust changing colour against the grain of thermodynamics, the question arises, is there intention inside matter? Not intelligence as we know it, but a structure of response so refined it mimics will. Science describes the universe through cause and effect, force-motion reaction. Yet the data from Atlas strains that sequence. Acceleration without venting, temperature shifts without corresponding emission, behaviour suggesting direction yet no agent to direct it. In such contradictions, speculation becomes a tool, not a weakness. Imagine for a moment that physical systems might contain a latent syntax, a way the universe speaks to itself through the shaping of energy. Could ThreeI Atlast be an instance of matter, briefly acting as message, a vessel designed not to travel, but to demonstrate? If the non-gravitational thrust is not an accident of outgassing, then the structure must store and release energy in controlled intervals. That implies regulation, and regulation implies logic. Whether that logic is born of biology, computation, or something beyond both, becomes less important than the recognition that motion itself can encode purpose. Perhaps intention is the wrong word. Perhaps the universe has always been performing a kind of thought experiment using mass and momentum as the grammar of awareness. The movement of ThreeI Atlast, then, is not will against inertia, but information translated into trajectory. From our limited vantage, we name such coherence mystery, but in another frame it might be simply physics extended to its philosophical edge, where every equation implies agency, and every particle participates in a conversation too subtle for language. To think that matter might think not metaphorically, but materially, is to stand at the threshold between science and wonder. In the faint blue arc of ThreeI Atlast, we glimpse not alien will, but the possibility that intention itself is a property of the cosmos. Every language begins with the naming of what shines. Long before equations, before instruments, humans named the sky not to possess it, but to belong within it. Light was the first boundary we recognized, the edge where the visible meets the unknowable. Now, as we study ThreeI Atlast, we are once again brought to that same frontier. Spectra wavelengths, photon counts all attempts to speak the name of light in the grammar of measurement. Yet no instrument captures the full meaning, because light is both the message and the medium, the question and its own answer. When the data returns from the James Webb Space Telescope, it will not arrive as sentences but as numbers, intensity over time, position ratio. Still within those numbers there hides a quiet syllable of recognition, a signature that whispers, "I was here and I saw you." Perhaps that is what we seek, not proof of origin, but communion through illumination. To give light a name is to declare kinship, to acknowledge that what we observe is also observing us, that photons crossing hundreds of millions of kilometers are not strangers but correspondents. The ancient astronomers spoke of lux photes, near each word meaning both brightness and knowledge. To them, light was not a phenomenon but a mind, the instrument of revelation. Modern science in its precision has not truly abandoned that belief. We have only translated it into equations. If ThreeI Atlast is indeed artificial, then its light is language, a deliberate composition across distance and time. If it is natural, then the same light still carries meaning, because meaning is not assigned, it emerges wherever perception meets pattern. So we arrive at the threshold of naming, not to label but to listen, not to define but to recognize. For every act of observation is an invocation, and every photon received is a word returning home. In this sense, the name of light is not something we invent. It is something we remember each time we look up, and as ThreeI Atlast fades into the outer dark, its radiance remains a question still glowing, waiting for the next observer to pronounce it. Every precise observation begins in a clean room, a space where dust, warmth and breath are controlled, where particles are measured by their absence. But there is another clean room, one no filter can create, the chamber of thought itself. To see ThreeI Atlast clearly, one must prepare not only the optics but the mind. In astronomy, contamination is not just physical, it is cognitive. Assumptions settle like invisible grains, belief in what a comet should be, expectation of what an anomaly must imply. Each fragment of certainty clouds the lens. Inside a literal clean room, air circulates laminar, steady, purified. In the mental equivalent, attention flows the same way, no turbulence, no noise of desire, only observation. It is the state scientists reach before a critical measurement, a mental vacuum stripped of conclusion, receptive only to light. Imagine standing beside a telescope dome before dawn. The temperature equalizes, the mirrors cool, your breath leaves no trace, the machinery hums in rhythm with your pulse. What you're preparing is not only an instrument but a condition of awareness. You're aligning inner atmosphere with outer space. This too is methodology. To think cleanly is as vital as calibrating a detector. A single bias can skew an entire dataset, just as a single mote can scatter a beam of light. The James Webb and Hubble telescopes operate inside controlled vacuums, their sensors shielded from heat and radiation. Human inquiry demands the same discipline, a vacuum of assumption, a shielding from the heat of belief. When ThreeI Atlast was first analysed, many dismissed its strangeness as data error. Others rushed to name it alien craft. Both reactions cloud the clean room. Between those extremes lies the posture of true seeing, neither denial nor fascination, but a neutral openness in which the phenomenon defines itself. To observe in purity is not detachment, it is devotion, because clarity is a form of care. In that stillness, both telescope and mind serve the same purpose, to let the universe reveal itself without interference. And so, the first step toward understanding ThreeI Atlast is to clean the space inside our own perception, until thought, like the lens, becomes transparent to light. Every precise observation begins in a clean room, a space where dust, warmth and breath are controlled, where particles are measured by their absence. But there is another clean room, one no filter can create, the chamber of thought itself. To see ThreeI Atlast clearly, one must prepare not only the optics but the mind. In astronomy, contamination is not just physical, it is cognitive. Assumptions settle like invisible grains, belief in what a comet should be, expectation of what an anomaly must imply. Each fragment of certainty clouds the lens. Inside a literal clean room, air circulates laminar, steady, purified. In the mental equivalent, attention flows the same way. No turbulence, no noise of desire, only observation. It is the state scientists reach before a critical measurement, a mental vacuum stripped of conclusion, receptive only to light. Imagine standing beside a telescope dome before dawn. The temperature equalizes, the mirrors cool, your breath leaves no trace, the machinery hums in rhythm with your pulse. What you're preparing is not only an instrument but a condition of awareness. You're aligning inner atmosphere with outer space. This too is methodology. To think cleanly is as vital as calibrating a detector. A single bias can skew an entire dataset, just as a single mote can scatter a beam of light. The James Webb and Hubble telescopes operate inside controlled vacuums, their sensors shielded from heat and radiation. Human inquiry demands the same discipline, a vacuum of assumption, a shielding from the heat of belief. When ThreeI Atlast was first analysed, many dismissed its strangeness as data error. Others rushed to name it alien craft. Both reactions cloud the clean room. Between those extremes lies the posture of true seeing, neither denial nor fascination, but a neutral openness in which the phenomenon defines itself. To observe in purity is not detachment, it is devotion, because clarity is a form of care. In that stillness, both telescope and mind serve the same purpose, to let the universe reveal itself without interference. And so the first step toward understanding ThreeI Atlast is to clean the space inside our own perception, until thought, like the lens, becomes transparent to light. Numbers arrive without emotion. They fall into memory like cold rain, magnitudes, flux ratios, albedo curves, each precise, each indifferent. Yet somewhere between those digits and the mind that receives them, meaning begins to take shape. For ThreeI Atlast, the data is pure spectral bands across ultraviolet, visible, infrared and radio, each returning values exact to 6 decimals, temperature gradients, angular momentum, colour indices. All of them whisper what happened, but not why. The question of meaning does not live in the photon, it lives in the space where perception interprets pattern. Science calls that process inference, but in its deeper sense it is contemplation. To turn data into knowledge, we must perform a translation from quantity into relation, from measurement into understanding. It is a slow alchemy, where the act of reading becomes an act of awareness. Each scientist at their console engages in the same inner ritual. They trace lines on a graph, correct for noise, calculate residuals, and in that repetitive devotion, a quiet realization forms that behind the order of numbers lies an intelligence not separate from us, but mirrored through our own logic. Meaning then is not extracted from the universe, it is co-created with it. The photon records the event, the observer completes the sentence. Data is half a conversation waiting for reply. In this light, ThreeI Atlast ceases to be merely an object of study. It becomes an interlocutor, an opportunity for dialogue between mind and matter. Its acceleration, its silence, its improbable blue are lines in a script that invites comprehension without conclusion. What remains is not certainty but coherence. We recognize patterns not because the universe insists on them, but because awareness and cosmos share the same geometry. So the work of turning data into meaning is not to solve a riddle, but to listen more precisely, to allow numbers to speak in their own rhythm. until they reveal what they have always contained, not messages from beyond, but evidence that understanding itself is a cosmic process. And when that realization settles, science and wonder meet not as opposites but as partners in the same sentence the universe has been writing since the first light. There are two ways of seeing. One measures, the other listens. One builds equations, the other waits. Between them stretches the quiet field where knowledge and wonder meet. Through ThreeI's Atlas, those two lenses have come to focus. Instruments recorded acceleration without exhaust color, without heat, motion without visible cause. Silence recorded something else that reality hides best when it refuses explanation. And when the analytic and the contemplative overlap, the image clears. To look through the scientific lens is to ask, how does this happen? To look through the inward lens is to ask, why does it move us? Neither question alone is complete. Only together can perception become understanding. A photon leaves a distant surface, crosses dust, and magnetic wind passes through the cold of 1 billion unlit kilometers and finally meets a mirror polished by human hands. We can trace that path in mathematics: energy divided by Planck's constant frequency, multiplied by speed arrival time measured to the microsecond. Yet none of that describes the moment the photon becomes perception, the instant when a number becomes a feeling, when light becomes awareness. That is where the two lenses meet. The physicist records, the observer reflects. Both actions complete the same circle, the universe witnessing itself through consciousness. For a heartbeat, measurement and meaning dissolve into one. 3i. Atlas drifts outward now past the sensitivity of our senses. Its orbit extends into interstellar dark. Its glow thins to the edge of perception. But traces remain. Spectra archived trajectories plotted the memory of that impossible blue. It lingers as both evidence and symbol, data and dream in the same line of code. Perhaps this is how the universe teaches humility. Not with thunder, but with precision, by presenting forms that exceed our definitions just enough to stretch us. Every unknown becomes a gentle instruction in perspective. We meet the unexplainable, and it adjusts the focus of what it means to know. Knowledge too orbits. It leaves the certainty of the familiar sweeps close to mystery and returns altered. We do not conquer the unknown. We circle it until our instruments become questions themselves. Each question reshapes the questioner. That is the true velocity of understanding. Light itself is the instructor. It never stops. It only changes form. It leaves one star, crosses the void, enters matter lens nerve thought, and ends as comprehension, only to begin again. This endless translation is the pulse of being, energy becoming awareness, awareness returning as curiosity. Every observation continues the same cycle. Data leaves its source, travels through distance, meets attention, and becomes interpretation. Meaning, like starlight, is never born from nothing. It is the echo of what already exists, revealed by time and patience. There is a spectrum to silence. The first kind is the silence of distant space so large that light itself becomes faint. The second is the silence of restraint, the choice to listen before concluding. The last is the silence that follows comprehension, when there is nothing left to add because the truth has completed its sentence. Those who tracked Atlas once feared this silence meant ignorance, but in the years since it feels more like invitation. A pause long enough for the mind to equalize with reality. In that pause, knowledge breathes. The universe speaks most clearly when we stop trying to translate it. So the observation ends not with an answer, but with a new discipline of presence. To know is to witness is to join what is known. Every photon recorded, every hypothesis refined is a mirror turned inward, proof that consciousness is part of the method. We are not outside the experiment, we are extensions of it. Two lenses remain: the scientific, precise, quantitative, sharp as geometry; the contemplative, wide, soft, patient as night. Used together, they turn analysis into communion. One measures the architecture of reality, the other measures the silence that holds it together, and somewhere between them meaning takes form. Now close the instruments, let the fans still the data streams, pause, the graphs flatten to calm, step outside the control room, breathe once into the same air that carries the starlight. Above you the sky is not distant, it is reciprocal. Every point of a light returns your gaze. You are part of the network of attention, a node in the universe's own act of awareness. When you look up, you complete a circuit begun billions of years ago. The light that touches your eyes is ancient, but the act of receiving it is new. That is how the cosmos renews itself through perception. We are not only observers, we are continuations. Our eyes, our instruments, our curiosity, they are the universe reflecting on itself. Every discovery is remembrance, every measurement a confession of wonder. A question remains soft and sufficient. What if discovery is not finding what is new, but remembering what the universe has always known about itself? That question does not seek an answer. It asks for stillness, and in that stillness the two lenses merge. Light fades, silence remains. We stay awake within it. The universe does not end in darkness, it ends in recognition, and in that remembering we become the light that looks back, and that quietly is enough.